Okay, so ladies and gentlemen, you are welcome. So in this video, we are going to look at the concept of heat transfer and the related formulas with work examples. So introduction to heat transfer. Heat transfer is the movement of thermal energy from one object or medium to another. So heat transfer is when a heat move itself from one point to another. That is what we call heat transfer. Let's say you have two objects, hot and cool objects, and when we rub them together, there's a likelihood the heat can be transferred from the hot object to the cooled object, and that is what describes heat transfer. So heat transfer is when heat or thermal means heat, so it's when heat energy is transferred from one point to another. That is what describes the heat transfer. Assuming now you have hot water with a cold water, so when you rub them together or when you mix them together, the heat can be transferred from the hot objects from to the cooled object. So the movement of water from one point to another, or from one object to another, or from one medium to another is what describes the heat transfer. Like for example, now let's look at this here. This is actually two different medium. So if you can see clearly from this medium, you will realize that we have, uh, you see the temperature here is very high. So when the temperature is high, so there is a likelihood there will be high energy collision between the particles. So, and this is the surface, and this is actually the environment where the temperature is very low. So now, ladies and gentlemen, if this temperature is moving from the medium where the temperature is higher to a medium where the temperature is lower, that is what described as a heat transfer. The Q here stands for the quantity of energy. So you can see that the amount of the energy is moving from the higher environment, sorry, to the medium where the temperature is very high to the region where the temperature is low. So that is where you have this sign in here indicating that the temperature or the heat is transferring from the hot object or from the hot medium to the cooled medium. So this heat transfer is primarily occur using three mechanisms. We have conduction, we have convection, and we have radiation. So these are the three major ways in which energy transfer from one medium or from one object to another. So understanding these mechanisms is essential for application in engineering, physics, and environmental sciences. So now let's look at conduction. So what is conduction? Conduction is one of the mechanisms of heat transfer in which heat is transferred through a solid material or between materials in direct contact. So when you have two solid materials, and the heat transfer from the hot materials to the cold materials, that describe as conduction. So conduction occur in solid material or between materials that are direct in contact. So that is what described as conduction. Like for example, let's look at this. These are actually the three different sequences of material A and B. And you can see clearly here, the temperature in the first material is 43 degrees centigrade. And then, so this temperature at 46 degrees centigrade is moving from object A, object B, where the temperature reduced to 39 degrees centigrade. So as the temperature moving from point A to point B, point C, the temperature will be actually decreasing. So ladies and gentlemen, what I wanted to say here is that you see here there are three different objects. They have the heat is moving from point A, point B, point C. So these are the two different solid materials. So this is actually a typical example of conduction. There are three different solid material where heat is moving from point A, point B to point C. It means that these are the three objects that are in contact. So the heat is transferring from point A go from object A to object B to object C because they are all in contact. So this is this. So then now it occurs, this conduction, it occurs at a molecular level where faster moving particles collide with slower ones, transferring their energy. So you can have a molecules where you can have many molecules. So those molecules that actually have higher amount of energy, they'll be transferring the heat energy or their energy to those particles that have lower energy. So because one thing that we should understand is that the higher the energy or the higher the temperature, the more the collision, and the lower the energy, the slower the collision. So when you have objects that have higher kinetic energy, that have higher temperature, then their kinetic energy, that is their movement, will be increased. And as their movement increases, then they'll be colliding with the slower ones, transferring their energy, making them also move faster. So the rate of heat of transfer by conduction can be calculated using Fourier's law. So using Fourier's law, the rate of the heat transfer by conduction can be calculated. So let's look at the law. So the Fourier's law is a law that tries to show the relationship between the heat rate transfer and the temperature gradient. So you can see the law here. The law states that the rate of heat conduction, which is Q, through a fluent layer is directly proportional to the temperature differences across the layer and the heat transfer area, which is A, perpendicular to the direction of Q, but inversely proportional to the thickness of the layer, which is the delta X. And the symbols is, so you see, ladies and gentlemen, this is a law that trying to show the relationship between quantity of electricity, the rate of heat by conduction. So it's directly proportional to the temperature differences, that is delta T, that is the temperature differences. So it's directly proportional to temperature differences and the area, that is times A, and inversely proportional to the thickness of the layer, that is the distance. That is the distance. So you see, whenever we have proportionality, then we remove it and introduce constant. So that is why now here we are going to have Q is equal to, we have Q is equal to K. So K is constant. And we have delta T. We have delta T times area. I need to delta T times area. Let me clean this so that I can write it correctly. So we remove proportionality and then we are now going to introduce constant. So the constant here is going to be, okay, we have Q and we have delta T. And then we have area divided by the distance. So this is actually the formula for calculating the rates of heat by conduction. So this delta T stands for the change in temperature, and that is T2 minus T1. So the T1 is the temperature of the hot object, while the T2 is the temperature of the cooled object, while A here stands for area, and then K stands for proportionality constant, while the Q here stands for the rate of heat conduction. So we said rate. So whenever we said rate, it means that we divide it by 10. Sorry, we divide it by T, that is temperature. That is the rates. So then, and we also have in some other textbooks, you will see that instead of this to state at this, they will tell you that the quantity of heat is directly proportional to temperature gradient and area. So what is temperature gradient? Temperature, whenever you had the word temperature gradient, it means delta T over D. That is change in temperature divided by distance. That is the temperature gradient. And the rate of heat by conduction stand for the quantity of heat because there is rate there. So Q is the same thing as Q divided by T because it is rate. So quantity of heat divided by time, that stands for the rate of heat of conduction. So I think, ladies and gentlemen, this is very clear. So let's look at the example. Let us consider two water columns at different temperatures. So one being at 40 degrees centigrade and the other being at 20 degrees centigrade. So as both the water columns are separated by a glass wall of area 1 meter by 2 meter and a thickness of 0.003 meter, calculate the amount of heat transfer, and the thermal conductivity of glass is 1.4 Weber milli per Kelvin. So you see, this is an example. So the thermal conductivity stands for K. So you can see that, ladies and gentlemen, from here we are given two temperature. So the two temperature, which is the T2, that is the final temperature, is 40 degrees centigrade, that is the temperature of the hot object. And then we have the temperature for the cooled object, which is 20 degrees centigrade. And then we have the area. So the area now is going to, because it is given in length. So remember, area is length times breadth. So we have 1 meter by 2 meters. So we are now going to say 1 meter times 2 meter, which is actually going to give us the 2 meter square. So we have area now to be 2 meter square. So we have 2 meters square. So then we have, and the thickness, which is the distance, is now going to be 0.0003 meter. And then the thermal conductivity, which is K, is now going to be 1.4 Weber per meter per Kelvin. So we have this. So since we have this, then the only thing that we are now going to calculate, the equation says we should calculate the amount of heat transfer. So Q is now going to be unknown. So we are now going to have Q to be our unknown. So Q is now going to be unknown. Then we are now going to take our formula, which says Q is equal to K area in open brackets T2 minus T1, then we close the bracket, then divided by the distance. So you can now see that the K is 1.4, and then the area is 2, then times temperature differences, which is in bracket, we are now going to have 40 minus 20, then divided by the distance, which is 0.0003. So after you have this, then you are now going to get your final answer. So let's look at how we work it here. So I think this is very clear, ladies and gentlemen. So this is how to get it. So let's look at exactly what we have. So from the work examples, we can now see that because I have already got the answer, so let me show you the steps. So this is just the raw methods of calculating the unknown. So let's see here. So you see the thermal conductivity of glass is 1.4. And then we can now see that the first temperature of the column, that is the hot, is 40 degrees centigrade. And then the temperature of the second column is 20, which is the cooled one. And then the area of the wall separating both the columns is 2 meters square, as I calculated. Then this is the formula. And then this is how we have the values. So we substituted them. So we have 1.4 times 2, and then this 20 is 40 minus 20, that is for the temperature difference, and then we have divided by 0.003, and then at the end we have 1000 or 18,667 watts. So then now that is for the conduction, the formula and the examples. So then the next thing is convection. So what is convection? Convection is a transfer of heat through fluids. So you see the other one, that is conduction, is a transfer of heat across solid materials. But this one is a transfer of heat in fluid material. That is, it can be liquid or gas, caused by the movement of the fluid itself. So the transfer of heat through fluid caused by the movement of the fluid itself. And this convection can be transferred into can be classified into natural convection driven by buoyancy forces and forced convection driven by external means like fans. So these are the different types or classification of convection: natural convection convection driven by buoyancy forces, and convection driven by external forces. So, ladies and gentlemen, the most important thing in convection is understanding how the heat is transferred in fluids, while conduction is the transfer of heat in solid material. So then the next thing now that we are going to look at is, of course, Newton's law of cooling. So the effectiveness of convection can be described by Newton's law of cooling. So according to Newton's law of cooling, state that the heat transfer rate, that is Q, is proportional to temperature differences between the surface and the fluid. So the heat transfer rate, which is Q here, the heat transfer rate, which is Q here, is directly proportional to temperature differences, that is change in temperature. So meaning that here, since we have proportionality, then we are going to introduce constant. So we now have Q is equal to K into temperature of hot minus temperature of cold. So you see, this is the formula. So the Newton's law of cooling said that the rate of cooling of an object is proportional to temperature differences between the object and its surrounding. Suppose T, that is, suppose T is time, and then the capital T is the temperature of the object, and then Ts is the surrounding temperature. So the following differential equation describes Newton's law as delta T over dt. So delta T over dt is the something as Q. So that is why Q here stands for E divided by time. So this is it. So you see, this is even an example. You see, suppose we consider 95 degrees centigrade cup of coffee in a 15 degrees centigrade room. Suppose it is known that the coffee cools at the rate of 2 degrees centigrade per minute when it is 70 degrees centigrade. So ladies and gentlemen, please, I wanted to work on this, and I want the answer on the comment section. Please answer this question and put the answer at the comment section. You see already key is given. So the key is given. No, it's not key. This T degrees centigrade per minute is for Q. So this is Q. And then the hot temperature is given as 15. And then the cold temperature is given at also 15. So what happens when the temperature, it reaches 70 degrees centigrade? So I'm now going to show you similar examples like this, but I wanted you to work on this, and please put the answer on the comment section. So then let's look at is similar examples, everything the same. A cup of coffee initially at 90 degrees centigrade is placed in a room with a constant temperature of 20 degrees centigrade. So you see the coffee has a temperature of 90 degrees centigrade and is placed in an environment where the temperature is 20 degrees centigrade. So after 5 minutes, the coffee cools to 70 degrees centigrade. It means that because of the room temperature is 20 degrees centigrade, then it's now actually give a final coffee temperature or mixture of the coffee to be 70 degrees centigrade. So you see, it's similar to this. You see this one after keeping it in the room, then it changed to 70 degrees centigrade. So let's look at how to calculate it. So by applying this formula, delta T by T is equal to minus K open bracket, temperature of hot object minus the ambient temperature. So then now we are now going to say that for the initial calculation here, we have to calculate K. So we need to calculate K. So find the cooling constant K using the first set of data. So the first temperature is 90 degrees centigrade, and then the ambient temperature is 20, and the time is 5 minutes. So you see, we start with the temperature of the mixture as 70 degrees centigrade. So we now have 70 degrees centigrade minus 90 degrees centigrade divided by, so this is delta T, that is the change in temperature. The change in temperature here means that the temperature of the mixture minus the initial temperature. So the initial temperature is, so the temperature of the mixture is 90, that is, or the final temperature after taking the coffee at a room of 20 degrees centigrade, then the temperature of the coffee cooled down from 90 to 70 degrees centigrade. So that 70 degrees centigrade, it means that the temperature of the coffee after placed in the room for the 5 minutes. So that is where we have. So after keeping it for 5 minutes, then it cools down to 70 degrees centigrade. So that is why here we have 70 degrees centigrade minus 90 degrees centigrade divided by 5 minutes, which actually gives us minus K open bracket 90 degrees centigrade minus 20 degrees centigrade. And that gave us, after the calculation, then it gave us K value as 0.0286 per minute. So we get the value of K. So how long will it take for the coffee to reach 50 degrees centigrade? So if after keeping it for 5 minutes, the temperature decreases to 70 degrees centigrade. So how long will it take to reach 50 degrees centigrade? So that is the second part of the calculation. So to calculate the time to reach 50 degrees centigrade, then we now say that, okay, the temperature of the mixture now, or the temperature after allowing the coffee to stay long, is going to be 50 degrees centigrade minus 90 degrees centigrade divided by delta T. And then we now have, already in the formula, we have minus, so we have minus 0.0286, then open brackets, the final temperature is 50, then minus 20 degrees centigrade, and that will give us the time to be 13.98 minutes. So this is actually after keeping the coffee for 13.98 minutes, then the temperature of the coffee will cool down to, or will reach 50 degrees centigrade. Okay, then, so you see, we have the formula for calculating, the heat transfer rate by convection. You also see the formula for calculating heat transfer rates by conduction. So then now let's look at radiation. So what is radiation? Radiation is the transfer of heat in the form of electromagnetic waves, primarily infrared rate. So you see, the other one, that is convection, is transfer of heat in a liquid medium. the conduction is a transfer of heat across solid medium, and then the radiation is a transfer of heat in the form of electromagnetic waves, primarily infrared radiation. So unlike conduction and convection, radiation does not require a medium and can occur in a vacuum. So radiation, it doesn't require medium. Convection require liquid medium. Conduction require solid medium, while radiation doesn't require solid medium or liquid medium. So it doesn't require medium at all. So, and can occur in a vacuum. So it can occur in a vacuum where there is no air. So then all objects emit and absorb radiant energy depending on their temperature and surface properties. So now let's look at the law, which is the Stefan-Boltzmann law. So the Stefan-Boltzmann law quantifies the power radiated by a black body in terms of its temperature. So you see that we have different types of body. It can be white, it can be red. So generally, black body absorb radiations more than any. So that is why sometimes if you wear black shirts, you used to feel very hot. So the formula used by Stefan-Boltzmann law, he used P is equal to epsilon sigma A times T raised to the power of 4, where P is the power radiated, epsilon stands for emissivity, while sigma is the Stefan-Boltzmann constant, and A is the area of the surface. So this law is crucial for understanding thermal radiation in astronomy, thermal insulation, and energy efficiency. So this is a Stefan-Boltzmann law that's trying to describe how solid surface, whether black or any color, absorb radiation. So this is the formula. We can see it clearly from here. The P stands for power radiated, and then the epsilon stands for emissivity, which is no unit. Surface area is area square, and then we have Stefan-Boltzmann constant, which is the constant value as 5.67 times 10 to the power of minus 8 Weber per meter square per meter square power 4. So the K power minus 4, that is quadrifold. Then the temperature is Kelvin. So let's look at another example. So a body of emissivity, that is E, is 0.75. The surface area is 300 centimeters square, and the temperature is 227 degrees centigrade, is kept in room at a temperature of 72 degrees centigrade. So using the Stefan-Boltzmann law, calculate the initial value of calculate the initial value of net power emitted. Net power emitted by the body. So this is simple, ladies and gentlemen. So we are now going to take the formula that says P is equal to epsilon sigma area then T raised to the power of 4. So this T raised to the power of 4, it can be changed in temperature, where like in this case we have 20 degrees centigrade, and then we have 27 degrees centigrade, and then for the initial one we have 227 degrees centigrade. So to do that, ladies and gentlemen, we are going to apply this formula. So we are going to have the temperature of hot minus the temperature of cold. Then so for epsilon, that is emissivity, is 0.75. So that is why here we have 0.75. And then for sigma, which is the Boltzmann constant is constant, it's already constant. So it's 5.67 times 10 to the power of minus 8 Weber per meter square K power minus 4. So this is what we have. And then for area, the area is 300 centimeters square. So we have to convert it to meter square. And that is why here is now changed to 300 times 10 to the power of minus 4 meter square. And then times open bracket the change in temperature. So the temperature is in degrees centigrade. So we have to convert it to Kelvin. So to convert it to Kelvin, we have to say 273 plus 227. And that is why here we have 500 Kelvin for the final temperature. And then for the temperature of the room, we have 273. Then we have to add it with 77, and that will give us 300. And that is how we get the 300 Kelvin here. So after imputing all this formula, you use calculator, and then you will find this as your final answer. So ladies and gentlemen, this is how to calculate a radiation. So ladies and gentlemen, I hope you will find this video very interesting. First, we look at the different types of heat transfer, conduction, convection, and radiation. And we look at the formula where we started with number one. We started with Fourier's law. Then we also looked at Newton's law of cooling. And then now we also look at the Stefan-Boltzmann's law. So you need to take this formula very careful, and then you try as much as possible to understand how to answer this kind of questions if you are given for both exam and test. So ladies and gentlemen, without wasting much of our time, we can also look at some heat transfer in phase changes. So phase changes involve the transfer of heat without a change in temperature, such as melting or boiling. So the latent heat of a substance is the amount of heat required to change its phase, which can be calculated using specific formula. So understanding phase changes is essential in processes like refrigeration, climate control, and material processing. So this is actually the phase changes by heat transfer. So you see, this is one of the application of heat transfer by phase changes. So I hope, ladies and gentlemen, you will find this video very interesting, and I hope you will subscribe and join to the YouTube community. See you next time. Thank you.